Hey everyone, in this video lesson, we're going to be doing some review. So it might seem like a review lesson, or maybe not, depending on how long it's been since you've taken your grade 11 physics course. We're going to review some terminology and speed and velocity in one direction. So let's get started. So the first thing we have to talk about is the difference between vector quantities and scalar quantities. So a scalar quantity is a quantity, and this you would learn in grade 11. It's a quantity that has magnitude but no direction. So something like mass, your mass is 80 kilograms. There's no direction associated with that. Like a time interval, like somebody ran the 100-meter dash in 10 seconds. What other example might there be? Energy, etc. Lots of different scalar quantities that you guys were introduced to last year. A vector quantity is a quantity that has both magnitude and direction. So some typical examples you would have learned in your grade 11 course, something like force. Force has magnitude, direction. And then you guys learned some new terminology, and we'll dive into this in a second, but things like position, displacement, velocity. Those are all vector quantities, and some of those have kind of scalar counterparts. And we'll talk about that in just a moment. So let's talk about first average versus instantaneous speed. So first of all, speed is a scalar quantity. And maybe before your grade 11 physics course, if you heard you might have even used speed and velocity kind of like interchangeably. But now we understand there's a difference. Speed is a scalar where we're only concerned with how fast we're going. Velocity is a vector where we're concerned with the direction too. So instantaneous speed is a speed at a particular instant. So, a car on the highway, maybe speeding up, slowing down. Its instantaneous speed is whatever you look at the odometer, and that's the speed. Average speed is the total distance of travel divided by total time. So like a car on the highway, it'd be maybe difficult to describe its speed at any given time if it's constantly, speeding up a bit, slowing down a bit. But if we knew how far the car traveled and how long it took, we could find an average speed. And average speed is just the total distance traveled divided by the total time, delta t. As a little bit of a side note, maybe you used a different notation in your grade 11 course, and that's fine. You can stick to whatever notation you're comfortable with, but I think this notation here makes sense. So let's do a quick example here. So at the Molson Indy race in Toronto, a driver covers a single lap distance of 2.9 kilometers at an average speed of 1.5 times 10 to the 2 kilometers per hour. So we're going to do a couple things. So one, we're going to review how to convert kilometers per hour to meters per second. And then we're going to just use our average speed formula to solve a problem. Now, I might solve A kind of the long way, and then that might lead us to a shortcut that we can just use all the time. So to convert this, I'm going to take, this is 150 kilometers per hour. And I'm going to write it like this, 150 kilometers per 1 hour. And I'm going to set up kind of a conversion chain. So I want meters per second, right? So the first thing I'm going to do is I'm going to make a little conversion to get this into meters. And we know that 1 kilometer is 1,000 meters. And the kilometers over kilometers are going to divide out. And so this will convert my speed to meters per hour. But I don't want that. I'd like seconds. So we can convert hours to minutes. So I'll write this. 1 hour is 60 minutes. And that gives me meters per minute. I want meters per second, so I'll do one more. 1 minute is 60 seconds. And that will get me meters per second. So if we do this, 150 times 1,000 divided by 60, divided by 60 again, let's see what we get. Times 1,000 divided by 60 divided by 60. So we get about 41.7 meters per second. Now, this can be impractical to do every time. You have to, you want your speed in meters per second. So if we look at what we did here, we ended up multiplying by 1,000 and dividing by 60 times 60, which is 3,600. If you kind of just reduce that, if you divide both of those by 1,000, you're left with 1 over 3.6. So the long and short of it is, if you want to go from kilometers per hour to meters per second, it's just equivalent to dividing by 3.6. And in the same way, if you want to go from meters per second to kilometers per hour, you can multiply by 3.6. So moving forward in the course, having done that conversion once, I don't need to do it more. I can just use that conversion factor of 3.6. So we've done A. So the average speed was 41.7 meters per second. What's the time in seconds to complete a lap? So V average equals distance over time. We can rearrange this for time. This means that time is distance divided by V average. And we know both of those things. So we have 2.9 kilometers. Now, just as a note, if our speed's in meters per second, we want to have our distance in meters as well. So that's 2,900 meters divided by the average speed, which we said was about 41.7 meters per second. And this will give us our time. So just a couple things to talk about too as we finish this one up. So 2,900 divided by. Now, if we do this, we're using our speed of 41.7 to 2 decimal or to 2 sig figs. If we wanted to keep more accuracy, we would have kept more decimal places, but I got 69.5. And then the more accuracy you keep in your speed, you'd get closer to 70. But to 2 sig figs here, we've got 69.5, and that would be seconds. Now, this is a side note as far as like calculations. Some physics teachers like you to leave in your units, and some don't. You don't necessarily need to do that. I myself, I don't need you guys to write in your meters per second, but some people, it makes them comfortable. You can check units as you go. So moving forward in my calculations, I won't always write in the units. I'll just understand that meters divided by meters per second will give me seconds. All right, so let's move on to talk about position and displacement. So these are two vector quantities, position, and we use the symbol D with the vector sign above. So as a side note, depending on what course you've taken, maybe you're used to writing your vectors with a little half arrow. It's the same thing. So, and to be honest, because I teach calculus and vectors normally, I might switch between the two, but they are equivalent. So don't worry if you're used to one notation over the other. So position is the distance and direction of an object from a reference point. So the difference between that and distance D would be, if I were to ask, well, how far do I have to walk to get to, this restaurant down the street? Maybe it says just 100 meters. You just have to walk 100 meters. But if I asked, like, where is this restaurant located? It wouldn't be enough to say 100 meters because you would need to know which direction to walk. So its position, it might be that it's 100 meters, north down the street or something. Displacement is a change in position. So displacement is kind of like a distance traveled and a direction. And so you would get that by subtracting whatever your final position is minus what your initial position was. And we're going to do an example of that in just a moment. Here we are. So here's an example we're going to do. So we have a biker traveling east in the diagram below. We're going to find the biker's displacement. Then we're going to ask, would we get the same answer using a different reference position? So note here that we're considering the biker's reference position to be right at this intersection here. And so initially, they're 338 meters west of the intersection, and finally, they're 223 meters west of that reference position. So we're going to solve the problem one way, and then maybe choose a different reference position and see how it works out. So let's give this a go. And again, in a question like this, and this will be a common theme, we're all coming from like different high schools, different teachers. So you might have just a slightly different way of doing things, and that's okay. So we're finding the displacement here, delta D. And we get that by subtracting the final position, subtract the initial position. And here we have the final position, 223 meters west, minus the initial position is 338 meters west. And right now, this is well set up for us. These are almost like terms, like you guys learned in your grade 9 math course. Because we're dealing with meters west and meters west, it's totally okay for me just to subtract these two quantities. So 223 minus 338. I know because they're in similar units and direction, I'm going to get an answer with the same units, meters west. So negative 115 meters west. That's kind of a weird way of saying that, because the biker obviously is traveling in the eastward direction. And astute observers would probably know the answer was actually already contained in the diagram. This is the exact same way. If you flip this negative sign, this is the exact same as 115 meters to the east. So our biker traveled 115 meters to the east. So this is one way to set up and solve a displacement problem. If you have a slightly different way of using notation, that's totally fine. So let's actually answer the question, what would we get if we used a different reference position? So instead, what if I used the biker's initial position as our reference position? So how would this change? Would it change the answer at all? You know what, guys? Green, not such a good choice in this background. Let's use a yellow. It should stand out better. So a good exercise would be, using this new reference position, what would D2 equal? What would D1 equal? So if you want to pause the video and think about that for a second, you can, and unpause when you're ready. But with this new reference position, and using our answer from before, D2, the final position, is actually 115 meters east of this new reference position. So D2 in this new scenario would be 115 meters east. And D1 is just our reference position, 0 meters east. And we can subtract those two guys, get 115 meters east. We get the same thing. So it doesn't matter what your reference position is. And I would encourage you, if you're given choice to choose a reference position, choose something that makes the math easier and just kind of intuitively makes sense, makes you feel comfortable. All right, let's move on. Talk about velocity. We've talked about speed, average speed, instantaneous speed. Let's talk about velocity. Velocity is a vector. It's the rate of change of position. So when words that should come to mind when you guys think about rate of change from your grade 9 course, maybe you think of slope. And when you see the word rate, rate is traditionally one unit divided by another, right? It's like a comparison of two quantities with different units. So let's dive in, and we'll hopefully you'll make more of that connection as we do an example or two together. Instantaneous velocity is a velocity of an object at a particular instant. Average velocity is the change in position divided by the time interval for that change. And so the formula would look like this. V average, and with the vector sign, we're talking about velocity, equals delta D, and here we're talking about displacement with the vector sign. divided by time. What you will notice too is that we are dividing a vector by a scalar. The result is another vector. Let's put this into practice. So we have our biker again. Let's find their average velocity. So they took 25.1 seconds to cover the displacement that we talked about earlier, 150 meters east, to go from D1 to D2. So I might do part A up here. So the average velocity, so V average, vector sign, is the displacement delta D, vector sign, over delta T. And here we have 115 meters east in our time of 25.1 seconds. And so you can see the units are going to be meters per second, and our direction is going to be east. So 115 divided by 25.1, about 4.58 seconds. Excuse me, 4.58 meters per second. And we are finding average velocity, so we do need to specify that direction to the east. So we understand that during that time, the biker might have been going a bit faster and a bit slower, but cumulatively, on average, for that time interval, averaging about 4.58 meters per second, traveling east. Let's do B. So if the cyclist maintains the same average velocity for another hour, what is the total displacement? So in this case, we're going to be rearranging that formula, and we're looking for displacement. That would be V average times delta T, just rearranging that formula. And we know those two things. So we have our V average, 4.58 meters per second east, and I'm including the units here. As I said, different students, different way of doing things. It's not the end of the world if you don't include the units here. I'm going to include it for this one. And our time is an hour. Now, if we want our displacement in meters, we need to be consistent with the units. So we need to have an hour in seconds. And from our earlier discussion with our conversion, we know an hour is 60 minutes and each minute has 60 seconds. That's 3,600 seconds for 1 hour. So 4.58 times 3,600. We get about 16,500 meters. So if they were to go for an hour, we could also say that's about 16.5 kilometers. That's how far they would travel. That's for part B. Now for part C, I might do this on the next screen just to save some space. So our cyclist turns around at D2. So after traveling that 25.1 seconds, at D2 turns around and travels to some position west, 565 meters west. So on my big blown up diagram here, where's my cursor? There it is. We're now going, somewhere back here to this new position. And the time it takes to go from this D2 to D3 is 72.5 seconds. So to find the average velocity for the entire motion, we have to figure out what the displacement is and what the time interval is. So let's do that for part C. Let's do time first, pretty easy. So here our total time for all the motion, we had 25.1 seconds from D1 to D2, and another 72.5 from D2 to D3. I should probably be able to do the mental math, but it's the morning and I have 2 kids, so I'm just going to use my calculator. So 97.6 seconds. What's our delta D? So let's use our skills from earlier. So our delta D, so our final position here is D3. Our initial position for the entire motion is D1. D3 is 565 meters west. D1 was, 338 meters west. And those are the same units. We have no problem subtracting them. 227 meters west. It makes sense because they're finishing more west than where they began. And we're now ready to find what this new average velocity would be for this whole motion. Delta D over delta T. We now have these things. 227 meters west. Total time, 97.6 seconds. And that's about 2.33 meters per second west. So let's just have a quick team talk. So during that motion, the biker traveled east and then traveled west. Their average velocity ended up being west. So for these 97.6 seconds, if another biker just traveled west at a very slow speed from D1 at 2.33 meters per second to the west, they'd meet up at the same spot. Now, let's just contrast this average velocity with the average speed. Average speed would be different. So this wasn't part of the question, but maybe let's just do a quick talk about it and just kind of scratch out this answer. So total time would be the same, 97.6 seconds. What would be the total distance traveled? So from D1 to D2, we got, let's just rough this out. So that was a distance of 115 meters. We've already worked that out. Now from D2 to D3, just kind of improvising here, 565 minus 223. That's a distance of 342 meters. I'll add little m's here, meters and meters. So if we just do that, 342 plus 115, the total distance traveled is 457 meters divided by 97.6 seconds. We get an average speed of 4.68 meters per second for the entire trip. So there's that example. We've talked about average velocity, compare that to average speed. Let's move on. So the other thing we want to cover in today's little review lesson is position time graphs, velocity time graphs. And then our next lesson, we'll actually talk about acceleration time graphs. We start talking about accelerated motion. So consider a runner running south at a speed of 5.5 meters per second for 3 minutes. So we've got a table of that data and a position time graph for that data as well. So what you'll notice, first of all, is that this position time graph is a straight line. And this is the first kind of note, something you guys learned in your grade 11 course. Is this, the slope. I'll just say of a DT graph, position time graph for short. It gives the average velocity. I'll add this note too. I'll just say this. A steeper curve equals a faster speed. And I just said faster speed because a steep graph or a steep curve could look like the diagram here, or it could look like something going down, right? Compared to maybe a shallower graph, steeper equals faster. But the slope of a DT graph gives the average velocity. Now, this particular DT graph was a straight line. So it wouldn't matter where we chose our 2 points and found the slope of that graph. We get the same average velocity. In this case, we expect to get 5.5 meters per second. Let's just try it out. Good review for finding slope as well. So to get the average, let's use, just to mix it up, I'm going to use the second and third points. So V average is change position over change in time, but I'm going to connect that to the slope of a graph here. So from this point here to, actually, I'll just use these middle 2 points. Yellow doesn't show up. There we go. I'm going to use these 2 points here. And this is just kind of reviewing your slope formula from your grade 9 math course. So we have 660, and then I'll include the units here just because. Meters south minus 330 meters south. Our time interval, 120 minus 60. So we're going to get 330 meters south over 60 seconds. And if you do that division, you do get 5.5 meters per second south, just as the question says. And you'll notice, like, if I had used the first 2 points, I would get 330 over 60. If I would have used the first and last, I'd get 990 over 80, which reduces to the same thing. So again, when your speed is constant, you can choose any 2 points you want and get that speed for that section anyway. What about velocity time graphs? So can you predict what the velocity time graph would look like for our runner, given their position time graph? If you want to pause the video and think about that, and I'll look at your lesson sheet. Unpause when you're ready. But here's what this velocity time graph would look like. It's actually a pretty simple velocity time graph because the runner's running at 5.5 meters per second. And for those 3 minutes, this is what it would look like. It's a straight horizontal line. We have a constant speed of 5.5 meters per second, a constant velocity because they're staying in the southward direction. So a couple notes for velocity time graphs. So we talked about the slope of a DT graph, position time graph gives. The slope of a velocity time graph and maybe you recall this from grade 11 course, is acceleration. We'll talk more about acceleration in our next video lesson. I'll add a little note here. A horizontal slope or a horizontal line indicates constant acceleration of 0. And we'll talk about the units of acceleration more. I'll just say meters per second here. And the last thing I want to talk about too is there's one more piece of detail that you can get from velocity time graphs. And it doesn't have to do with the slope of the VT graph. It has to do with the area underneath the curve. The area under a VT graph gives displacement. And that makes a lot of sense, actually, if you consider the graph we have here for our runner. This is just a rectangle. And if you do 5.5 times 180, it'll be 5.5 meters times 180. You get exactly 990, the displacement of our runner over these 3 minutes. So those are the big ideas you guys should have coming into the course. Slope of VT graph is acceleration. In this case, because it's horizontal, we don't have our runner standing still. They're just moving at a constant speed here because the acceleration is 0. And then the area under VT graph gives displacement. Finishing things up, let's talk about non-uniform motion. The graphs we look at right now, they're pretty simple, just straight lines. So here is a table here. The data is graphed of over 8 seconds of some non-uniform accelerated motion. So here we have the position in terms of meters of this car speeding up from rest, moving forward. So if you just want to think about it for a second, how does the graph indicate that it's speeding up? So if you want to pause and think about that for a moment, or maybe you've got it right now. But if you recall, we talked about that, in a DT graph, steeper means faster. Well, here we can see that, if you think about the slope of this, let me move my handsome image up a little bit. Get out of here. I want to get a color here. Get out of here, face. There we go. If we think about the slope, initially it's horizontal, which makes sense, right? So if we start from rest, not moving, the slope should be 0 to give us the speed of 0. And then we have it moving kind of, if you just think about the slope, it's getting steeper and steeper and steeper, faster and faster and faster. So this getting steeper indicates it's speeding up. Let's find the average velocity of the car over the first 8 seconds. So we have the tools to do that. So we can't find this. This isn't a straight line that we can find the slope of. But what we can do is we can find the slope of, the formal math word is secant. So we have a curve and we have 2 points on that curve. If we find the slope of the line segment joining them, we could find the average speed. So nothing really new from the previous example. It's just we're choosing 2 points on our line. And it does kind of matter which 2 points we choose. This is going to give us the average speed from 0 to 8 seconds. If I did a line segment from, say, 4 to 8 seconds, it would give me the average speed from 4 to 8, which would be faster than from 0 to 8 because this car is speeding up. But let's get this done. Let's make sure I have a color that will show up. For part B, average velocity is displacement over time, or thinking of it as the slope of that dashed line, that secant I've made. So we have 64 meters forward minus 0 meters forward. And our time interval, 64 minus 0, 8 minus 0, gives us 64 meters forward. And I'll add in the seconds there, over 8 seconds. And we can see the average speed, 8 meters per second. We covered 64 meters in 8 seconds, giving an average speed of 8 meters per second. Now the question is, how could we estimate the instantaneous velocity at a given time? Because if I wanted the speed at a certain point, finding the slope isn't going to cut it because I need 2 points to find the slope. And if I want to find instantaneous velocity, that's just at one particular point. So how do we kind of resolve that? So the idea is the instantaneous velocity is given by the slope of a tangent. So this would be the last little note we make today. Instantaneous velocity is the slope of the tangent. And I'll just add quickly too on a dt graph, on a position time graph. So if you grab 2 points, like for example, this blue dashed line, this would give you the average velocity as you move from the 2 seconds to 8 seconds. The green dashed line would be the average velocity from 2 to 6. The looks like black dashed line would give you the average velocity from 2 to 4. And as you shorten up that time interval, you might notice that the slope between those line segments becomes pretty close to the slope of a tangent. A tangent is a line that hits a curve just one time. And as you make that time interval smaller and smaller and smaller, that average velocity gets pretty close to the instantaneous velocity. So that's this notation here. This is the idea of a limit. For those of you who haven't taken calculus, which would be a lot of you, some of you guys might just be coming out of the grade 10 course. This just basically is saying make delta t small. So as delta t gets smaller and smaller, that average velocity, which is equal to delta d over delta t, displacement over time. As you make time small, you get closer and closer to the instantaneous velocity. For now, given a dt graph, if you did require that instantaneous velocity, we are doing a bit of estimating. You just might have to draw the tangent and find the slope of it. Later on, when you learn calculus, you'll have techniques to actually mathematically determine the instantaneous velocity. But for now, what we need to know is the slope of the tangent. All right, everyone. Those are the big ideas for this review lesson. In our next review lesson, we're going to talk about acceleration, acceleration time graphs, and then solve some one-dimensional acceleration problem or kinematics problems that involve acceleration in one direction. And for most of us, that'll involve the big 5 kinematics equations. All right, guys, I hope you're staying well. Hope you have a great day, and we'll see you soon.